Hello. So this is a active RC filter. So it's called an active filter because we have an input voltage and output voltage that can increase the signal's power rather than just decreasing it based on the frequency. So we have an inverting amplifier which creates a negative gain, and then we also have a capacitor which is responsible for creating that impedance that filters out the lower frequencies. And here we have the wave-gen graph. We took a network sweep, and we see here that although the power source takes a while to get up, the output, the gain decreases and decreases as frequencies get higher, and it's flat for lower frequencies. And if you look really closely, you can see that the gain is actually above zero, where in the passive filters, the maximum gain couldn't exceed zero, but since there's this external power source, the signal is able to become stronger by a power of around 6 or 7 decibels, and that explains why it's above zero. Over here we have the theoretical calculations for the frequency. So we have the 3 dB drop-off point is the maximum, which we calculate to be 6.44. Subtract 3 from that and solve from the frequency where we're at this level, and we get about 19 kilohertz. And if you come over here, we measured using the interpolation feature and found that the experimental 3 dB drop-off is about 18 kilohertz. Or frequencies, up until this 3 dB drop-off point where you start to see dramatic changes in the gain, you also see changes in the phase because phase is related to the frequency as well. And we're back. We have now a high-pass filter. The difference between this circuit and the other one, which is still over here because we're using it in the next part, is that the capacitor and the resistor are in series with each other, where before they are in parallel. So this causes a high-pass filter, an active high-pass filter, rather than the low-pass filter. So this will filter out the lower frequencies, as you can see over here. So you can see here we have our graph of the high-pass filter, where higher frequencies are a flat line and the gain is above zero, which means the signal is being amplified. And as you get down here to lower frequencies, you really start to see that filtered out, especially at the 3 dB point, which we measured to be 19.9 hertz, not kilohertz. And we calculated a very similar number over here, 19.3 hertz. And we have a different phase here than the last one. We have at the lower frequencies, it's higher, and then you see a dramatic change right at the same point where the gain curve also has a dramatic change, and as you get past that, it's more flat. Last but not least, we have a combination of the previous two circuits. So now the input for the right-hand high-pass frequency filter is connected to the output of the low-pass filter. And this causes the effects of both of these two filters to be combined. As you can see over here, we have the low-pass filter, and then it's high, 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 and then drops down again for the high frequencies. And you can see on this graph we have the low-pass filter's 3 dB point is very similar to the one we measured previously, 9.8 hertz. And if you come over here, we have the 3 dB point for the high-pass filter, which is slightly different than what we got, but it's probably because of some kind of systematic error. It is 17.54 kilohertz. And as for the phase, we have dramatic changes at both 3 dB points of the low-pass and high-pass filters, which is to be expected because both of their effects are combined.